I'd love for you to like break down for us, how is a GPU different from the Trainium versus Inferentia chips, as well as how these differ from TPUs, tensor processing units that we hear about, as well as IPUs, these, I think, intelligence processing units. So there's like all these different kinds of accelerators that we can use for deep learning, and I think more are emerging all the time. So yeah, break down for us like the differences.
Yeah, absolutely. So when we started looking into inferential and trainium, we basically stepped back and asked ourselves, how can we build a chip that is optimized for deep learning workloads from the ground up? So let's not take any dependency on previous architecture. Let's see how we can do it in an optimized way. And our observation was that in both CPUs and GPUs, there's still an energetic overhead to performing computations. And what I mean by that is that they run instructions, and whether it is with a small number of very advanced cores or with a very large number of more or simpler cores, they fetch an instruction from memory, they decode the instruction, and then they perform a relatively small computation and write the result back. So when you look at the energetic breakdown, only about half of the energy is spent on the actual computation, the floating point multiplication and addition that we need to do. So we looked for ways to solve it fundamentally via a different chip architecture. And we stumbled into actually an old architectural concept called systolic arrays, in which you basically you layer what we call PEs, or processing elements, next to one another, and then you structure the computation like an assembly line. So basically, there's one we fetch one instruction, decode it, but then we perform one computation, move the data to the next processing element, perform another computation, move the data to the next processing element. And with a decently sized systolic array, that's how the architecture is called, we can get to a point where 99% of the energy consumption is on the actual computation that we need to do, and not on instruction decoding
Whoa.
and fetching.
That sounds like an insane increase from 50% to 99%. I was expecting like kind of like a marginal increase in
Yeah.
something like, but that's like it's a completely different situation.
Exactly. And we felt that this is fundamentally something that we need to bet on, and we basically structured a matrix engine on this underlying architecture. Now, interestingly, GPUs also started incorporating similar ideas over time with what they call tensor cores. These are also systolic arrays, just smaller ones. We can talk about them later. But the first idea that we had with inferential and trainium is that we need to leverage systolic arrays. On top of that, the other idea that we had is that it's much easier to program a small number of large cores if you make them efficient enough compared to a very large number of small cores. So we kind of wanted to get the best of both worlds with CPUs and GPUs. So make sure that we run at lower voltage and then very high energetic efficiency, but at the same time, make sure that we have a small number of cores so that the software programming is much easier. And we did that as well with inferential and trainium, along with all kinds of other optimizations to kind of accelerate deep learning workloads end to end, because it's not only matrix operations, it's much more than that.
Wow. Very interesting. So then, okay, so this kind of gives me a sense of the GPU versus Trainium Inferentia difference. So TPUs, IPUs, how are those different from these other options?
Yeah, let's talk about that. So basically, in recent years were kind of golden years for chip architects, because all of a sudden this deep learning workload came in and it's extremely popular. It's exploding in the amount of compute demand that it requires, and now people get to rethink how we should build compute units for this workload. So
Mhm.
there's a couple of architectures that emerged over the last couple of years. TPU is one of them, and it's very similar in the fundamental architecture to what we do with Trainium and Inferentia. It's based on a systolic array. It has a set of supporting vector engines that we can talk about later. But I would say that TPU sits on the same camp as Inferentia and Trainium, while other architectures like IPU and a few others take a different approach where the main idea in that architecture is that we want to avoid reading and writing data from memory at all costs. So basically that they build what's called a data flow architecture, where you read the inputs from the memory, but then you pass inputs from one engine to the other and try to avoid writing data to memory at all, throughout the computation. Now, there are pros and cons with that approach. The advantage is that you can build a more cost-effective system if you can do it right, because the memory system is quite expensive. So you can kind of oversubscribe to some extent your memory system, or even have a very cheap, low bandwidth memory system. But the downside, as I see it, is software simplicity. Because now, as we program these chips, we need to make sure that we take into account how the data flows from one engine to the other, and make sure that it never gets to a point where some of the compute units are idle because they're waiting on the neighboring compute units to get free or something like that. So it adds some softwaring challenges that need to be solved.
Very interesting. So, yeah, so the pro with a TPU is that it can be cost efficient because of how they've optimized to try to have data flows uh, moving into memory and out of memory. But the con of that is that there's extra complexities, and if that could mean that some of these processing units are sitting idle.
Yeah, that's for IPUs, but yeah.
Oh, for IPUs. Yeah, my bad.
Yeah. For for TPUs are not data flow architectures. They have at the heart of them, they have a very efficient matrix computation engine, but they are supported by a very high bandwidth, high performance memory subsystem to move data in and out of this efficient matrix engine.